Today I'm happy to be here to give a talk on the k-means-based consensus clustering. And the first thing I want to talk about something about myself. Again, my name is Hongfu, and I'm a Chinese guy. And Hongfu in Chinese means tons of good luck. So hopefully I can bring good luck to you and your department. Currently, I'm the tenure track assistant professor at the Department of Computer Science at Brandeis University. Before that, I hosted the master and the bachelor degree in Beihang University, major in management. And also I have 2 minor bachelor in applied math and law. And after that, I changed my major from the management to the computer engineering and graduated in 3.5 years. And I'm so lucky to get a position at Brandeis. And I also have 2 internships. One is in the Microsoft Research Asia, and the other is in the Adobe. And something about my research. Actually, I have 2 research interests. The first thing is I will focus on data mining, machine learning fundamental problem. This problem is not proposed by me, proposed by some big name maybe 20, 30 years ago, and it's very challenging. What I'm doing is just to simplify this problem to make it simple. For example, today we will talk a topic on the spectral ensemble clustering. It's an algorithm with a time complexity n cube and the space complexity n squared. And I transform the problem and solve it in both the linear n time and space complexity. So it's just like to see shortcuts in the algorithm. And the other is I will focus on some interesting applications, emerging topics. For example, currently I'm doing some translation between the image and music. And also I will do some translation between the sign language and speech, something like this. And so you can see this is my T-style research style. So you can see I will focus on the k-means optimization. And with this, we will go really deeper. In this talk, we will talk the k-means-based consensus clustering, spectral ensemble clustering, infinity ensemble clustering, and tons of branches in terms of the balance clustering, constraint clustering, domain adaptation, feature selection, outlier detection, blah, blah, blah. And I have some honor. For example, we got the first prize award in the international conference on computer vision. Is a test on the human face to recognize the face from 1 million people. And also nominated as the KDD top 20 reading star, maybe in 3 years ago. Okay. So this is the outline of today's talk. I will talk about what is cluster analysis and what is consensus clustering. And I will deliver 3 topics on the k-means-based consensus clustering, spectral ensemble clustering. If we have time, we will talk a little bit about the infinity ensemble clustering and other related topics. So what is cluster analysis? Cluster analysis is a fundamental technique in data mining and machine learning. So from this picture, we can see the cluster analysis is just want to separate a bunch of instances into several groups. And within the same group, the data points are much more similar to each other. The data points from different groups, they are dislike. And the cluster analysis is totally unsupervised task and has widely used applications in terms of the bio, file, image retrieval, social media, blah, blah, blah. Even in our daily life, cluster analysis is also very popular. For example, in the digital marketing, we want to segment the customer into different groups. And within the same group, we want to design some strategy to do the digital marketing. And we can also use the cluster analysis to do the city planning, outlier detection, to segment the image into the silver pixel, even segment the image into the citizen part and the background, blah, blah. And we can also use the cluster analysis to do the big data visualization for the network. And in the recommendation system, we want to find the similar users. And and also we can use the cluster analysis to do resource reorganization, blah, blah, blah. And in our recent research, we use the cluster analysis to do the image co-segmentation. Here we have the input is several related images. So you can see in the images we have the common objects is the car, right? So what we want to do is without any supervision information, we want to segment the car. And you can see this is our result. Here is a car, here is a car, here is a car, here is a car, here is not a car. So we want to remove the outlier, something like this. And this is the class analysis for the outlier detection. And here we have several flight trajectory.
Just out of curiosity, when you take your second image of the car, why doesn't it cluster on something like the building in the background? How are you differentiating those two things?
Oh, this is a really good question. So this co-segmentation is we want to segment the common objects.
So it's the image-to-image comparison.
Exactly. For example, if in these several images, they also have the same building, we also want to segment. And for the next application is we want to find some outliers for the flights. So you can see every trajectory is the one flight. And we have several cities, Seattle, San Francisco, blah, blah, blah. And we want to see here, there are three groups, but we still have some outliers. We want to find what is the outlier. What's the problem with the flight? What's the problem with the sensor? Blah, blah. And back to the cluster analysis, one of the most simple and famous clustering algorithm is named the k-means clustering. The k-means clustering is a partitional clustering algorithm, and one of the famous solver is named Lloyd k-means. For the Lloyd k-means, it has the two iterative steps. The first one is we want to find the k centers and to assign each data points to the nearest centroid, and the other is to repute the centroid by the means. So you can see this is the objective function of the k-means. Here, x is the data points, and the mu is the centroid. So what we want to do is we just want to find k centroid to minimize the distance. And here is a figure show how k-means works. So at the very beginning, we randomly select three data points as the centroid, here, here, here. And then for every data points, we will calculate the distance between this data point and the three centroids. For example, if we look at this data point, we calculate the distance from here, 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 here to here. This is the nearest one. So we color the data points as green. And we do this kind of process for all the data points. So you can see all the data points has been colored. This is the step one. And step two is to calculate the centroid. So we look at the green cluster, so we calculate the centroid. Centroid should be here. So see, to move to here. These two steps iteratively continue until converge to this kind of stuff. So to my best knowledge, k-means clustering is the simplest, also the fastest clustering algorithm used widely in both academic and industry, because there are several properties, good properties of the k-means. The first one is very simple. The second one is very fast. And sometimes we also want to say k-means is robust to some extent. Why? I know there are some drawbacks of the k-means. For example, k-means is sensitive to the outlier and blah, blah, blah. But in general, k-means is also very good for some real-world applications.
And you specify beforehand how many clusters you want, right?
Yes. So this is the one parameter of the k-means. We need to predefine the cluster numbers. So you can think about this is the parameter. So here I also want to say, someone want to say that this is one of the drawbacks of the k-means, but I don't think so. The reason is everything needs input, right? So we do not think about the parameter is the drawback of the k. As far as I can see, any clustering algorithm wants the hyperparameter. Even for the hierarchical clustering, we also want a threshold to make the tree to be several branches. So for the k, it's also hard to decide, I admit it, but for some other parameter by some other clustering algorithm, it's also hard to tell. But for the k-means, there are tons of study on the k-means study, so we also have some hierarchical way to choose the k in the suitable range, something like this.
Is it guaranteed to converge?
Yes, k-means is guaranteed to be converged.
Is that ever done with something other than an L2 norm?
Yes, we will talk about it.
You're going to talk about it?
Yes, we will talk about it later. Yes, k-means is guaranteed to be converged. And actually, there are two famous solvers. One is the Lloyd k-means, we just talk about here, and the other is Hartigan k-means. the difference about the Hartigan k-means and the Lloyd k-means, you can think about here is the Lloyd k-means is calculate the centroid by batch. So what that mean? That means here, for every data points, we calculate the centroid, the distance between the data point and the centroid. And in this case, the centroid is fixed. So this is the Lloyd k-means. And for the Hartigan k-means is, for example, here, this data points, the nearest centroid is here. So we need to update the centroid. So every data point, assign the label, we need to update the centroid. So we can think about the Hartigan k-means is update the centroid every time.
So because you're specifying k, so if you initially start with something, so you basically every time you run your model, you run your k-means clustering every time with a different k until you get a good result, sort of as a you use trial and error to determine k.
Oh, we have several ways to determine k. For example, as you mentioned, we can use the objective function value of the k-means to determine k. With different k, we can draw this kind of figure, and this x-axis is the objective function value of the k-means. This is the k, and the y is the objective function value. So this curve something like this. So we will pick this kind of k to choose the cluster number. We also have several other ways to choose the k. Okay? So k-means is the simplest clustering algorithm, but the cluster analysis is so popular. There are tons of clustering algorithms has been proposed based on the different assumptions. For example, for the k-means, it's based on centroid. You think about all the data points can be presented by only k centroid. This is good enough. So I do not care about all the data points. So what I care about, only 3 centroid is good enough. So this is the assumption of the k-means. And we have different assumptions. For example, we can base on the connectivity, we can base on the distribution, density, subspace, even graph. So here is the thing. We have many clustering algorithms. And why we need consensus clustering. So cluster analysis is a totally unsupervised clustering task, right? So what that means? That means we do not know what is the ground truth, and we do not know the partition we got is good or not. So different algorithms return different results. We do not know which is good, which is bad, and some algorithm has several parameters you need to train, and some suffer from the low robustness. So in the real practice, what we need is, I cannot guarantee this algorithm is get very good performance on every scenario, but in general should be good. So for the unsupervised task, what we want is really robust one. So we need consensus clustering. So what is consensus clustering? Consensus clustering, also known as ensemble clustering, also cluster aggregation, which found a single partition agrees with several basic ones. So there are some problems of the basic single clustering we have talked about. So the advantage of consensus clustering, the biggest advantage is robust. It can lower the risk from your weird data distribution and lower the risk from the improper algorithm parameter. And sometimes on average level, it can help us find a better solution and can be conducted distributedly, can be do the data privacy, not reuse, blah, blah, blah. So let's look at this figure. Think about this is our data points. We have a bunch of data points, and we first need to generate the basic partitions. So we can think about here, we can use k-means on the data sets to generate several different basic partitions. You can think about here we can use k-means with k equal to 3. Here we can use k-means k equal to 4. Here we can use k-means k equal to 3 with different initialization. And for the consensus clustering, we want to fuse these 3 different basic partitions into an integrated one. Okay, here is some notation. Okay, let's rephrase it again. That's the capital X denotes the data set, and we have several different algorithms, even the same clustering algorithm with different parameters. And we have a bunch of basic partition, pi I to the pi r, and the goal of consensus clustering is we want to fuse the full basic partition into a consensus one. Here I want to mention a little bit. So the task of clustering analysis is we want to separate the data points into different groups, right? This is the goal of the cluster analysis. And here, the task of consensus clustering is we want to fuse different basic partitions into the consensus one. The inputs of the cluster analysis and consensus clustering are totally different. So here we can see for the cluster analysis, the input is just the data points, X. And for the consensus clustering, the input is a bunch of basic partitions. So you can think about the basic partition can be generated by the k-means with different k, by different clustering algorithm, and by some algorithm with different parameters. We do not care about the consensus clustering. For the consensus clustering, the input is just a bunch of existing basic partitions.
So for the same data set, you have different kind of partitions. So which means you need a lot of pre-computing to
Yes.
get it.
Yes. For example, here we can use k-means with different k, and even the same k, different initialization, we got 4 basic partitions. And we want to fuse these 4 into one. So what that means? That means for the cluster analysis, it's a partition problem. And actually, for the consensus clustering, it's a fusion problem.
In the k-means with the same number, you mentioned the initialization of it. So the answer you actually get does depend on where you randomly choose the initial set of centroids?
Yes.
That doesn't sound robust. Okay.
But we also have some way to handle the sensitivity of the k-means. The very easy name, k-means plus plus. Okay? So let's go back to the consensus clustering. Okay? So the goal is we want to fuse these 4 basic partitions into the consensus one, and this problem is very challenging, even much challenging than your expectation. Why? Different from, we have another term is ensemble classification. Here, we focus on the ensemble clustering, totally no supervision. We do not know which direction we should go. So this is one challenge. And the other challenge lies in the nature of the clustering. For example, if we look at pi 1 and pi 2, for the pi 1, the first 3 data points are in the class 1, the next in class 2, the rest in class 3. And we look at the pi 2, the first 3 in class 2, and the next in class 3, and the rest in class 1. And actually, they are the same, right? For the partition, we do not have the label. What does that mean? That means we have label 1, 2, 3. You can also label it 2, 3, 1. So we do not have the semantic label. This is apple, this is banana. No, we only have the number. So what does that mean? That means in the cluster analysis, the label can be permute. Even after permute, they are still the same partition. So we need to handle this. Okay? If we look at the pi 2 and the pi 3, for the pi 1 and the pi 2, we know, okay, this class 1 is mapping to the cluster 2, okay? And we look at the pi 2 and the pi 3. This class 2 is mapping to here, or to here. Hard to say. And we look at the pi 3 and the pi 4. They have different cluster numbers, even more challenging, right? So the consensus clustering has been proposed maybe 10 years ago, but still very challenging problem. Okay? In the literature, there are 2 categories to handle the consensus clustering. One is with the explicitly objective function, the other is without. Okay, we will talk it one by one. And the first one is from the definition of the consensus clustering. Consensus clustering wants to find a single partition which agrees with the basic partition as much as possible. So the keyword is agree. What does agree mean? Agree means similarity, right? We want to find a partition is similar to every basic partition, right? So here, we use a utility function to measure the similarity between your basic partition and the consensus one. But here, I want to mention, previously we used the similarity, we will transform into the distance function, right? And we talk about distance function coming in our mind is the square Euclidean distance, cosine similarity, KR divergence, blah, blah, blah. But here, I want to mention this kind of distance function is measure 2 data points, right? And here, we want to measure 2 partitions with n data points with a similarity, and the partition can be permute. The orders, something like this.
So just so I understand what you're claiming, Or what is it that you're claiming that ensemble clustering can do that, say, normal k-means can do? So, for instance, I think the counter examples for k-means usually is like the Swiss roll data set or like the smiley face data set, where just geometrically you can't get the clusters. Are you saying that with consensus clustering, you'll be able to hit the geometry of the data better, or like it'll naturally adapt to say like the true metric of the data?
This is a good question. For the cluster analysis, is totally unsupervised, right? And actually, we do not know the results is good or not. But on average level, the consensus clustering provides better performance than the single clustering algorithms. We will show some experiment results later.
So what's the size of R compared with N?
Size of R compared
Like
with
basic
N.
partition, like number of partitions.
Oh, this is a very good question. We will talk it later. Usually, we will choose the R equals to 100.
Whatever data points.
For any data points. For n R equals to 100 is good enough to get a robust result. And then later, we can make it to the infinity. We will talk it later.
Also, I have another question. To make the basic partitions, should we use many different clustering algorithms, or you should keep on the one, like if you choose k-mean?
Oh yeah, so this is a good question. But for the simple and fast, I will choose k-means with different k.
Oh.
Okay?
And you think that
it's good enough. So let's go back for the first category. We need a utility function to measure the similarity between basic partition and the consensus one. But here, the utility function is measure the similarity on the partition level. It's not on the distance level. Not on the distance level. So how to handle this? So we use the constraint matrix. For the constraint matrix, we can see in the consensus partition, you have k cluster. And in the basic partition, you have ki cluster. And this number donate the data points. Both belong to these clusters. And we have this kind of table. Based on this kind of table, we can design some utility function to measure the similarity between the pi and the pi I. So one of the famous utility function named the categorical utility function, something like this. So for the first category, the challenge lies in how to design a very effective utility function to measure the similarity between the basic partition and the consensus one. And the other is how to solve it, right? So you can see, gosh, it's so complicated. How to solve this problem?
So what's the P here?
P is just the n divide the NII blah blah divided by the total number. So this can be probability from 0 to 1. Okay, let's focus on the first category. So first category is we propose a k-means based consensus clustering, and from its name we can see, yes, we just use k-means. The simplest clustering algorithm to solve this challenging problem. And from the left side is consensus clustering based on the utility function. Is a complex problem, time consuming, and then in the right part is k-means clustering. It's a well-defined problem, has the good property, for example, convergence, blah blah blah, and very fast. Nearly linear time complexity, and by this we can enjoy so many benefits. For example, the right part is very simple. We have theoretical support. We have the general good performance. We can handle the heterogeneous data. We can handle the large scale data. We can handle the integrated data. Blah blah blah. How can we do this? For example, this is the input of our consensus clustering. We have 4 basic partitions. And the first step is we want to do the 1 of k coding transformation to get the binary matrix. For example, here, the x3 in pi 2, the class number is 2, so we will transform into 0, 1, 0. So we just run k-means clustering on the binary matrix. And we can get the same performance with the consensus clustering with the categorical utility function. Let's go back a little. So if VR utility function is the categorical utility function, so we can just run the k-means on the binary matrix with the squared Euclidean distance. They are exactly the same. But we are care about, for the categorical utility function, we can run the k-means. And the k-means is nice, right? It's very fast and very simple. And our question is, what other utility function can also enjoy the k-means form? So we propose the KCC utility function. We give a sufficient and necessary condition tell about what kind of utility function is the KCC utility function, and you can transform into a k-means with what kind of k-means distance. Not only with the square Euclidean distance, we can use other k-means distance. Okay. Before we talk about it, we have two lemma. The first one is if we run k-means on the binary matrix like this, and this is the centroid. And what that means? That means let's look at the categorical utility function. Given the basic partition, and the second term is a constant. And what is the first term? And the first term, we can say this part is just the jth element in the centroid. So this is the link between the consensus KCC utility function and the k-means. And the other lemma is we want to find the relationship between this part and this part. So we introduce a strictly increasing function g to make them to be equal. Yeah. Based on this two lemma, we provide the KCC utility function. So a utility function just like this kind of form, and we can call it a KCC utility function. And for this kind of utility function, we can solve it by the k-means with this kind of k-means distance. For example, the previous one, the categorical utility function, is something like this, and we can just solve this problem on the binary matrix, use the squared Euclidean distance. If we have the utility function based on the entropy, its corresponding k-means distance is the summation of the KR divergence on each basic partition. So we can see, actually, we can design some utility function. And here, he gives us a convex function phi. We can design a utility function, and this utility function is a KCC utility function. And correspondingly, we can know what is corresponding k-means distance.
Sorry, perhaps you can understand. Why does running k-means on the binary matrix solve that permutation invariance problem?
Yes.
Why?
Because, so here, we can think about here the utility function. I can give you a little explanation. So here, after we do the transformation into the binary, right? So here we have the 1 0 0 0 1 0, and here we have the 1 0 0 0 1 0. So we want to calculate the distance, the x1 and the x2. Their distance is 0, right? And for example, if we permute the label as 2 2 2, 3 3 1 1, and there will be 1 1 here.
Yeah.
So the same story. So you can see on the binary matrix, we can keep the permutation, something like this. Okay, this is the theorem of the KCC utility function. So by this means, we give a sufficient and necessary condition about what is the KCC utility function, and the secret is the phi. It's a convex function phi. And based on the KCC framework, we do two extensions. The first one is how can you use the KCC to handle the missing data. For example, here is our input. We still have the full basic partition, but we have several missing here. And what we do, the first step is we still do the binary transformation, and with the missing part, we transform the all zeros. But here, be careful, they are not all zeros. We just mark them as all zeros, right? So in our framework, we think about the missing value. The missing label here provide no utility. And what that means? That means in the k-means framework, the missing data points do not contribute your centroid. So we update the centroid like this. And we use this kind of centroid, we redefine the utility function. We found, there is one more parameter. And what this parameter means? This parameter means the completeness of the basic partition. For example, we look at pi2. Here, we have two missing. and this number is 5/7. What that means? That means in our KCC framework to handle the incomplete basic partitions, this incomplete basic partition, its weights are naturally turned down. This is also makes sense, right? So for example, the weight of the pi 2 is 5/7, and the weight of pi 3 is 1. So in this kind of case, the weight of the incomplete basic partition can be naturally turned down. There will lead to our next extension. Can we automatically learn the weight of the basic partitions? So we want to give different basic partition different weight to get some good results. So can we do this? So we add another term, it's a weight learning term, something like this. And can we solve it? For example, we can fix the weight. So this is just the consensus crossing. We can solve it by the k-means, right? And we can fix the consensus crossing, and this part will solve by a weight learning part. And let's go back to the question. Can we automatically learn the weight of the basic partition? And our answer is yes, we can, but actually we do not need to do that. Interesting, right? We will talk it later in our experiments. So here are some experience of the KCC, and we show different utility function have the different performance. And here we recommend the entropy-based utility function. It has a better performance. And you can see KCC is very fast, and in sense, KCC is just a k-means, and no one runs faster than k-means. So we compare with the state-of-art algorithm at that time, okay? And KCC enjoyed high efficiency and robust performance. And we do some extensions. For example, we analyze the number of basic partitions, the number of R, right? And we found here the x-axis denotes the number of basic partitions. For example, if we only use 10 basic partitions to generate the consensus one, and we run the algorithm 100 times, and we do the box plot, so you can see we suffer from large variance. But we use more and more basic partition, the performance gets better and better, and keep still, something like this. So here is the question: how many basic partitions I should generate, right? This is very challenging because we have several ways to generate the basic partition. You can use k-means, I can use special classing, we can use different parameters. But we have this kind of phenomena. With more and more basic partitions, we have the better performance. So we have some crazy idea. How about to do the infinity consensus classing? We will talk about it later.
But your performance drops off every so often. No. It's not uniformly improving as you go up.
Okay, but we have some theory to talk about it. Here is we have the ground truth, right? And we do the external evaluation, but actually we do not know which is good, which is bad. Okay, and for the second one, we go detail into the quality of the basic partitions. Here we have the ground truth, and we know which basic partition is good, which basic partition is bad. So we have 100 basic partition, and we sort them from the highest and to the lowest. And here we draw two lines. And this blue line is we gradually remove some, okay, let's see that again. We gradually remove some low quality of the basic partition. For example, here we have 100 basic partition at the first point, and the second one is we remove the worst basic partition. Here we have 99 basic partition, and here we have 2. Okay, this is the blue line, and the red line is we do the opposite. We first remove the high quality basic partition. We remove the best one, and here we only have 2 worst basic partition. So we can see this is the phenomena. Is the blue line keeps still, and the red line after some threshold drops, something like this.
What is the quality there? Like,
Well,
is the weight, or how did you
What is
define
quality?
the quality of the base?
We have the external measurement. For example, every data set we have the ground truth. We have the label. We use the label to know which is the high quality basic partition, which is the low low quality basic partition. Here is very interesting. For example, we look at the blue one. Blue one is we gradually remove some some low quality basic partition from the left to right. But we can think about from the right to left. What that mean? That means we gradually to add some low quality basic partition into our pool. Right? Here we have two. And we gradually to add some basic partition into our pool to do the consensus. But here we only add some low basic partition. Here low one, even lower, even lower, even lower, the worst one. So we keep still. Well, what does that mean? I'm good, I'm strong, I'm robust, good enough. I do not care about these bad guys. So these bad guys cannot hurt me. Bless you. So that's the reason why we want to use consensus clustering. It's so robust. It can robust to the bad guys.
But for the blue one, at first we need the good quality.
We will talk about it later. Okay? The quality we will talk at the red one. So the red one is we gradually remove some high quality of basic partitions. So it keeps a while and drops. So what does that mean? That means on the first glance, it seems, yeah, the good quality basic partition is the key to the success of consensus clustering, right? But actually not. Why? We go to detail for this data set. For this data set, we generate 100 basic partition, and we go into detail. Only 10 of them, the performance is larger than 0.5. A 90 basic partition is below 0.5. So what does that mean? That means you can see from 100 to 90, and from 90 to 80, and from this period, we do not have any good basic partitions, but we still have some good performance. So what does that mean? That means from this stage, there should be some other factor to factor the performance of the consensus clustering. That is diversity. So here, so the quality and the diversity of the basic partition are the key to the success of the consensus clustering. And what does that mean? That means diversity is different, right? So I cannot improve myself only by myself. So if I want to be success, and I'm the guy to do the clustering and do the consensus clustering, I found another guy also do the consensus clustering. We talk about together. What I know, he knows. What he knows, I know. Nothing new, right? But when we talk about some other researcher in other department in the bio, geo, blah, 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 even we have a different views. And after some spark, we have some new idea, blah, blah. So that's why the quality and the diversity is the key to the consensus clustering. After few fusion, we get the better performance. And here we talk about the generation strategy and the performance on the increment basic partition, blah, blah, blah. And the other is about the weight learning part. Remember about the weight learning, we want to assign different weight to the different basic partitions. And the right bar is the weight of each basic partition. Here we have 100 basic partition, and the blue line shows the quality of the basic partition. We have the ground truth. We can calculate every basic partition. So we can fit these two lines, and the coefficient is very high. It's nearly 0.75. So what does that mean? That means in our framework, we can automatically assign high weights to high quality basic partitions, right? So we can, and we can assign low weights to the low quality of the basic partitions. This is quite good, right? But after we use the weighted basic partition to fill them together, we found the problem. For example, here is the lambda, is the hyperparameter to control the consensus part and the weight learning part. And for this part, lambda is very small. Here we do the weight learning. And for the lambda is very large. You can see the right line is the standard deviation of the weight is became to 0. So you can think about the right part equal weight. We do not do the weight learning. And the left part, we do the weight learning. You can see with the weight learning, the performance is 0.25. And without weight learning, everything is equal, nearly 0.7. Why? So here, we have good performance, right? Is within our expectation, we assign high weights to high quality of basic partitions, right? But here, after we ensemble them together, the performance is disaster. Same phenomenon on another data set. So, same story. We cannot improve yourself only by yourself. Why they are high quality of basic partitions? Because they are similar to the ground truth, right? Several basic partitions, they are so high. That means they are very similar. After we ensemble them together, same story. Most of them are similar. So after we ensemble them together, we cannot get the high performance. So we just use equal weight. And we demonstrate, okay, here we demonstrate with the equal weight, our basic partition has more diversity. So diversity actually is the key to the success of consensus clustering, because we cannot guarantee we can have some lucky enough to have some high quality of basic partitions.
So you actually show the lambda equal 1 to 5 on the top left figure.
Here?
Top left figure.
Uh-huh.
And like compared with the bottom figure, it seems already pretty like low standard deviation, right?
Uh-huh.
So is it same performance, similar way, like if you plot like 7 to 10 to 3, like then like you also have like high weight for high quality?
No.
I mean, I didn't understand like why you show like 1 to 5 on the top one.
Oh, here we just
Bottom one is already like very low.
Mhm.
Your standard deviation is pretty low. Like. But you explain like top one is you say like the quality and weight is good correlation. Bottom one.
Uh-huh. I know, they are on the different data sets.
Ah, so this is different.
Mhm.
So what you mean is that if you do the weight learning, it can give like big weight to the high quality partition.
Yes.
But it will not help you for the clustering,
For the ensemble.
upon ensemble clustering,
Mhm.
because they are very similar to each other. So,
Exactly.
so you mean like you do not, turns out to be like you do not need to do the weight learning.
Exactly. So in the practical, we just use equal weight. So everything is very simple, right? K-means is simple, weight learning is simple, something like this. Okay, let's do the small summary. So here we give a theoretical study on the KCC utility function, which lead the consensus clustering into the simple K-means solution. And we provide the sufficient and necessary condition. And we do two extensions to handle the incomplete data and discuss the weight learning part. And we also do some applications on the text learning and the pan-omics gene expression. Okay, we have to fast a little bit. Okay, here we talk about the second topic is the spectral ensemble clustering. Remember, there are two categories of consensus clustering. One is based on the utility function. The other is based on the coefficient matrix. What does that mean? That means the first step is we want to build a coefficient matrix. Here is the input of our basic partition, and we will transform into this kind of matrix. And this matrix calculates how many numbers, how many times a pair of instances occurred in the same cluster. For example, if we look at x3 and x2 in the first basic partition, they are in the same cluster, and then in the second partition, they are in the same cluster, and then in the third partition, they do not in the same cluster. In the fourth partition, they are in the same cluster. So you can see here the number is 3. So this matrix directly calculates how many times a pair of instances occurred in the same cluster. And what does that mean? If we divide this matrix by the number of basic partition 4, And the meaning of this matrix is directly calculated what's the probability a pair of instances should be in the same cluster. Right? Previously, we want to calculate the similarity matrix based on some distance, kernel, something like this. You can see here, we directly use the coefficient matrix. We can calculate the probability of a pair of instances in the same cluster. So, in this view, this matrix can be regarded as the similarity matrix. And for the second step, any graph partition method can be conducted on the coefficient matrix from the final consensus clustering. So for the second category, the advantage is they transform the consensus clustering into a graph partition problem. So remember, consensus clustering is a fusion problem. It's not a partition problem. But we can use any classical graph partition method on the coefficient matrix. So this is a huge advantage. But the drawback is for the graph partition method, they suffer from the huge time and space complexity. For example, we need to build the coefficient matrix, right? It's n times n. And sometimes for some graph partition method, they suffer from the n cube time complexity. So our solution is we propose a spectral ensemble clustering and short for SAC. So what is SAC? SAC is directly apply the spectral clustering on the coefficient matrix. Here is the objective function of the SAC, and you can see it's actually very similar to the standard spectral clustering, except previous spectral clustering used the Laplace graph, and here we replace with the coefficient matrix.
Why do you need to make this objective function?
This objective function is the spectral clustering objective function.
To measure the similarity?
Mm-hmm. So for the spectral clustering, I can talk a little bit. It has two kinds of objective function, and it also has the minimal one. So for the spectral clustering, is given the graph, they want to cut some edges to make the graph disconnected, and they want to have the minimum cut, and also to make the disconnected graph to have the even size.
I mean, what's the relationship between this objective function with the previous matrix that you introduced, like the probability matrix?
Okay, so this is a probability matrix.
Yes.
Mm-hmm. So you can see what we do is we just use the standard spectral clustering. We replace the Laplace graph with the coefficient matrix. But here is the thing: no magic happens, right?
What's the D?
D is the diagonal matrix of the S. So here only the Z is unknown. So you can think about this is just a standard spectral clustering. We just replace the input. But here I want to mention no magic happens. Why? In this kind of solution, we still need to build the coefficient matrix and run spectral clustering, suffer from the n cube time complexity, or another disaster. But why we still focus on SAC? Because we have an elegant and equivalent way to solve this problem efficiently. So we found a short path. So we build a link, and this is the SAC, and this is the weighted k-means. We found they are equal. So what should we do? So given the binary matrix, we want to run the weighted k-means on the binary matrix, and the weight of each data points is the summation of the size of each cluster. For example, the x1 in pi 1 in the first cluster, and how many data points in the first cluster? 3. x1 in pi 2 in the second cluster, the cluster size is 3. x1 in pi 3 in the first cluster, size is 2. x1 in pi 4 in the first cluster, size is 4. So the weight of x1 is 3 plus 3 plus 2 plus 4 is 12. And we run k-means not on the binary matrix. We run the k-means on the binary matrix divided by its corresponding weight. So we demonstrate this part is equal to this part. And you can see we can use this kind of way to solve the SAC into a weighted k-means. By this means, we can dramatically drop the time complexity from n cube to the linear n. And also, from the space complexity, we do not need to build the coefficient matrix. What we need is just the binary matrix, right? And to be honest, the binary matrix, we do not need all the zeros. We just need which position is non-zero, it's fine. So actually, this dimension of this matrix is only 4. So for the space complexity, we also drop from the n cube to the linear n. And you can see for the KCC, it's based on the utility function, and for the sec, it's based on the coefficient matrix. But actually, we can use the objective function of the sec to derive its Euclidean its own utility function. So you can see from the utility function, it measures similarity of two partitions, right? And coefficient matrix is measures similarity between two data points. And here we build a bridge between these two kind of methods. And we can say the similarity on the instance level and the partition level can be interconvertible. And we remove the slides. We are also to give the theoretical analysis on the generalizability and the robustness on the sec. And we do tons of experiments, and we demonstrate sec is good and sec is very fast. And we do some experience and to demonstrate and to extend the sec on the multi-view scenario. And we do some applications on the Weibo data. You can think about the Xinlang Weibo is a Twitter-like service in China, right? And we want to cluster tons of tweets and to find some interesting event. But here is the thing. The tweets, we have really many tweets, and after we remove some advertisement, we still have 60 million tweets. And we use some keywords to have 10,000 dimensions. Here you can see here is the big data, right? So at the very beginning, we do not think the consensus crossing is suitable for the big data. Why? We need to generate the basic partition first, right? And we need to generate the basic partition 100 times. Even for k-means on this kind of data is a disaster. And we want to run 100 times, get the 100 basic partition, and fill them together. So this is not a good idea. But special ensemble crossing or the consensus crossing is all very robust. Not only robust to the outliers, to the parameters, also robust to the incompleteness. What does that mean? That means we can use some row segmentation to get partial data. For example, we can randomly select a sub-data set to get a basic partition and do this 100 times. And fill this incomplete basic partition for sec. And in this way, we do this kind of data cluster, and we found some interesting events. For example, the first cluster to demonstrate that school begins, right, in the September. And the second cluster tell about the traditional Chinese Mid-Autumn Festival. And the next cluster talk about the conflict between China and Japan in the historical event in September 18. And this is a famous social event at that time. Famous Meng Ge apologized for her science crime, and this is about happy blah blah blah. Okay, so this is a small summary about the special ensemble clustering, and we propose sec and uncover the equivalent relationship with the k-means, and we also build the bridge between two category consensus clustering algorithm based on the utility function and based on the coefficient matrix. And we also do some robust generalizability for the sec and to do the incomplete basic partition for the big data analysis. Okay, we can quickly go over the infinity ensemble clustering, and we have this kind of phenomena, and with more and more basic partition, we have the better performance. Not means better, we have more robust, stable performance. So our crazy idea is how about generate infinity basic partitions? This is crazy. We cannot generate infinity, and we cannot fill them together. But we have this kind of theory is with the number of basic partition goes to the infinity, the coefficient matrix became stable and stable. So what that means? That means actually we do not need to calculate infinity basic partitions. What we want is just the expandation of the expandation of the coefficient matrix. This is what I want. So, but here is the thing, we also cannot to calculate it in advance. So what should we do is we want to put the expectation of the coefficient matrix during our optimization. And we found, this kind of is infinity ensemble crossing. We want to generate infinity basic partitions. And this is a very famous architecture in deep learning, is marginalized denoising autoencoder. So we found actually, in this case, we can calculate the expectation. What we do is we crop the basic partition and then marginalize them together for the expectation. So this kind of process is exactly to add drop-off noise to our basic partitions, to make our basic partition to be incomplete and then marginalize them together. So you can see the total paper have 5 lines code, 4 lines from the marginalized denoising autoencoder, 1 line from the k-means. Okay, and then we found we do some experiments. We found here the IEC is also very fast. Okay, and sometimes has good performance. You can see even 5 basic partition, the IEC performance is all very good because we generated the infinity basic partition representation even with 5 basic partitions. And we do some applications on the pan-omic gene expression analysis. And here is the 13 cancer, and here is a different basic partition algorithm. But we do not have the ground truth here. We do not have the ground truth, but we use the survival analysis to measure the performance. So we carefully tune the p-value to be 0.05 to be white. And some warp color means it passed the survival analysis. Some cool color means it failed. Okay, so you can see IEC warm is very warm, right? And we have 13 data set. We have 4 different handful of views in terms of protein, mRNA, scNA, and totally 13 times 4, 55. And for the 55 data set, IEC passed nearly 40, and the second best is less than 20. But here is the thing, even for the same cancer, in this kind of view, IEC fail. This pass, this fail. So here is the question, what kind of view, what kind of data I should use to analysis? So the question is, you can use all of them. Right? We fill them together and use IEC rank again, and we pass all the 13 data sets. Okay, so this is the topic about the consensus clustering. Here is some my roadmap. So previously we do the KCC, and we extended to handle the spectral ensemble clustering, to handle the infinity ensemble clustering, and extend the k-means to the fuzzy sequence-based consensus clustering. And we also do the simultaneous clustering and the ensemble. We also use again to generate more diversity to increase the performance of the k-means of the ensemble clustering. And beyond the consensus clustering, we also do something related to the structure preserver learning in terms of the field selection, heterogeneous domain adaptation, partition level constraint clustering, interpretable clustering, and some applications such as the image co-segmentation, zombie user detection, outlier detection, blah, blah, blah. Okay, here are some other topics, but we do not think we have enough time. Okay, in this talk, we talk about 2 categories of consensus clustering. No matter what kind of type, we can easily transform into the k-means based algorithm in the elegant and efficient way. It's just like to seek the shortcuts in the laboratory. Okay, thank you for listening.
Okay, thank you Hongfu for such a good talk, and I think it's quite easy to follow. And because we are short of time, maybe like 1 or 2 questions.
I'm curious, if you just gave this class of algorithms just white noise, is there a measure which tells you that there is no clustering going on in this thing?
Oh, this is a good question. So for the k-means clustering, you can give anything out of them, but I don't think if you just give the white noise, it can still give you some result, but this result doesn't make any sense.
I'm just wondering whether there's a measure that says this doesn't make any sense or not.
I'm not sure if you have the external measurement that you can measure it. So here is the thing. For the cluster analysis, we totally unsupervised, right? So for the evaluation, we have two ways. One is you have the ground truth. You can use external measurement. And the other is we do not have the ground truth. So what should we do? Just like the survival analysis, we can use the partition results put into another applications. Use another application, we do the evaluation. Something like this. But for the white noise, I don't think it's good. So the difference between the classification and the clustering, even they have the label supervised and not supervised, something like this. So here is the key. For the clustering, it focuses on the structure. And for the classification, they focus on the boundary. For example, even for the white noise, and if you have the training data, have the positive and negative samples, you still can write the curve at the boundary to separate the positive and negative data points. But for the clustering, no structure, no way.
Any other questions? I have a question.
Mm-hmm.
So what's the performance of the proposed method to the image segmentations? So because, I mean, I just recently read some paper in Job Science, and
Mm-hmm.
people do image segmentation for the fault detections.
Okay.
And people use like CNN or like deep neural networks, this kind of method to detect the fault. Basically, it's just giving you an image of the subsurface.
Okay.
You find the fault in that image. So I was wondering what kind of performance your method will be when you apply to the image segmentation.
Oh, this is also a very good question. For the image segmentation, we just finished this kind of work, and we have a intern from China work on this project in 1.5 months and work it. And in this kind of image segmentation, we provide zero assumption of the input and achieve the current state of the best performance. If you are interested, I can share the paper and the code to you.
Okay. Any other questions?
Okay.
So if anybody have any other question or want to talk with Hongfu in person, we still have a lot of time during the afternoon, so you can just come. Yeah. Okay, let's thank Hongfu again.
Thank you for listening.